Thank you, Madhu. Let me just share my screen. Is my screen visible, Madhu?
Yes, Mathew, you can go ahead.
Okay. Hello, everyone. Welcome to the session. In this session, I'll be walking through the various subsystems in Sunbird and do a deep dive into some of the tech components that drive them. We'll also be trying to touch upon how these components are glued together to create an internet scale system that is elastic and resilient and can also be managed easily at scale. Before we get into the tech details, I would like to recap on some of the key architectural principles that drive us and our thinking at Sunbird. I hope you have all watched the Sunbird overview and architecture session by Dr. Pramod Verma, where these are covered in quite detail. I just want to highlight some of the key factors when it comes to any tech choice in Sunbird. They are observability, security, scale, and resilience. Okay, and we move on to look at what are the thoughts on Sunbird. So Sunbird is a ontology-driven, API-driven, and data-driven system where we try to adopt open specifications where possible and also extend them where we think that they do not meet our needs. Okay, moving on. So we are going to start looking at the various tech stacks and the subsystems. Now, when you look at the tech stacks, you can see that we are using a plethora of tech stacks, all of which are open source. We do try to use the best tool for the job while also trying to standardize the usage of the stack along with its best practices across the board. Okay. Moving on to the subsystems. What you're seeing here, they are the various subsystems in Sunbird. At the base, we have a strong foundation built on DevOps and Infra best practices. We have 100% automation in everything we do, 100% ability to monitor the state of the infra and systems. And we also have log aggregation and log tracing to enable that each of these subsystems do not have to take care of all these concerns, cross-cutting concerns. Talking about the subsystems, I also want to take time to explain why we think of these as subsystems. We think so because each of them are a collection of generalized microservices which are extensible and can have an independent evolution. So at the base, we have the knowledge platform, which actually takes care of the taxonomy, the content management, and dial. We then have the data platform, which gives us the observability through telemetry, and there is significant amount of data processing to generate analytics and reports. We have the user org system, which actually manages users, organizations, handles the role-based access control and authentication on the platform. We have tracking and credentials, which takes care of, so we've seen that knowledge platform manages content. The knowledge platform also allows us to group content to create collections, and the tracking and credential subsystem enables us to make these collections trackable. It also allows us to do batch management. Batches are groups of people who are probably participating in a trackable collection. And we also are able to issue certificates based on various criteria towards the end or completion of a course or collection. Talking about collaboration, we have the ability to create groups of users where they can actually engage in various activities and collaborate over discussion forums. We also have a chatbot capability where we are able to allow users to interact with the bot with natural language understanding to understand more about the system and discover content on the system. And the top layer is an array of client tabs. We had a session by Santosh and Namrita on the client reference client architecture. So we have a portal. We have mobile app and the desktop app for user consumption. And within the portal is embedded a content framework, which actually allows the creation and playing capabilities of content. Moving on. So we'll now start looking at what are the constituents, the tech components that are leveraged in each of these subsystems. And then we would, look through each of the subsystems and see what forms them, what drives them. So the knowledge platform is an ontology driven platform with a directed graph for knowledge representation. All the content, assets, questions are objects in the graph and are categorized to multiple taxonomies. And Neo4j is used to represent the graph. Those of you who have attended the content hierarchy deep dive session by Railu yesterday have seen how flexible the taxonomy and the content model is and how it can be easily extended for your use cases. The content model also allows storing external attributes, which we are storing in Cassandra, and the assets, for all content is actually stored on blob storage. Redis is leveraged as a pass-through cache, where we try, the microservices try to store data with a TTL, which is configurable for low latency reading needs. And the ontology engine actually generates events for all changes that are made to the graph. So when you add a new content, when you add a new relation from a collection to a content, or when you add a new asset, these are all changes to the graph, and these are all generated, all of these generate audit events, which are available in a pipeline. And by generating these events, it gives the ability for other consumers, and other subsystems to leverage and understand the changes and react to them in a required fashion. It also is key to allowing the extensibility of the platform. And one use case I can think of is these audit events are actually used to sync the changes that happen on the graph into the Elasticsearch index, which actually drives the search capability. There is also a published pipeline, which actually takes care of the content lifecycle, packaging for offline use, and handling the video streaming use cases. So, we put quite an emphasis on ensuring that all the content types, barring maybe few MIME types like YouTube, are packaged for offline use and can be, and our client apps are actually configured to use them offline and play them offline in areas of low network coverage. Okay, we are using Samza jobs to drive some of these pipelines, which take care of enrichment, and also the audit event indexing into Elasticsearch is actually done through Samza jobs. Okay, and moving on to the next subsystem, which is the data platform. Observability is key in any scalable architecture. All interactions with any of our subsystems in Sunbird generate telemetry, which adheres to a very tightly controlled specification. The telemetry service accepts compressed, batched telemetry events and ingest this to a Kafka pipeline. And we have a series of jobs, a series of data pipeline streaming jobs, which actually process these events and eventually ingest the data into Druid. So Druid is our strategic OLAP store, and Superset is used as the visualization engine on top of Druid to ensure that users have a real-time visibility into what's happening on the system and the patterns of usage on the system. The events are also compressed and backed up to blob storage for long-term storage. These backups are also used by the various analytics data products, which are Spark jobs, to compute the necessary summaries and metrics, which are again ingested into Druid for visibility on the patterns of usage on the system. We also have a device registry, which helps to store device metadata and location data, which is declared by users who are mostly anonymous. And this data actually helps us denorm, we've spoken about in earlier sessions, we've spoken about how telemetry is, designed to not have any of the PII information. It is designed to just have a bunch of IDs, and it's on the server side that we actually enrich these events through denorm to enhance them for additional information. So the device registry actually helps to stamp the location data onto these events during the enrichment. The data pipeline lays a solid foundation for any data processing that is necessary on a scalable system, and it has the necessary automation and extensibility where you can customize it for any of your use cases. Okay, moving on to the next subsystem, which is user and org. So Sunbird is designed to be a multi-tenant system, and the user and org subsystem allows representing the various tenants as organizations and allows mapping users to these organizations with specific roles. The user org data is stored in Cassandra and it's synced to Elasticsearch, again leveraging audit events. And it is Elasticsearch which actually powers the search capabilities. Like in the knowledge platform and other subsystems, we use Redis where necessary as a pass-through cache to have low latency reads. The user auth system also takes care of authentication. It actually integrates with Keycloak as its OpenID Connect provider. While Keycloak comes with a lot of features out of the box, we wanted to leverage the federated user store capability in Keycloak to ensure that the user data stays within the user subsystem and not in Keycloak's data store. And we've used custom Keycloak service providers to ensure that the integration of Keycloak with the system is purely via APIs. And this gives us the flexibility to decouple the user model changes with the authentication process as long as the APIs are backward compatible. And it also allows us to do things like encrypting the data, the PII data at rest that is stored within the user system, with that being transparent to the authentication system in Sunbird. We also support various types of authentication at the moment out of the box. We support email and phone based and password based login. We also have integration with Google Sign-in, and we also have a custom sign-on single sign-on implementation, which can be easily adopted by any other system to allow users who are logged into their systems to come into Sunbird. There is a prior handshake required between Sunbird and the external system before this can happen. But it's quite extensible there as well and customizable. And the authentication stack is built in a way that it can be easily extended to integrate with other OpenID Connect providers or custom protocol providers as well. Another key facet of the user org subsystem is notifications. All of us know how important notifications are when you want to convey, when you want to reach out to your users. And we have, ready integration with SMTP, SMS, and Firebase cloud messaging out of the box. And we also support, multiple types or modes of notification. You can use real-time notifications for things like OTP distribution. And you can also, we also have a batch mode or async mode notifications, which are used for more of, the notifications which can be eventually delivered to the user. Like, let's say a user has completed, a trackable collection, and there is a certificate that you've issued and you want to let the user know, you could use the async notifications, which are batched and processed. And like all of the other subsystems that we'll see, each of these APIs or microservices also create audit events for any changes that are incoming. And you can create consumers to listen on these audit events and build out your use cases or react to them. And Kafka is used as the audit event, pipeline, and the Samza jobs are used for processing these events. Okay, moving on to the next subsystem, which is tracking and credentials. The tracking and credentials. So I spoke about how we could have, cohorts of people or batches of people, who are wanting to consume a trackable collection, and we want them to be able to allow them to resume playing from where they stopped earlier, and also be able to see their progress. So the tracking subsystem takes care of ensuring that the progress state can be updated into a user's, store, and it can be used for progress tracking. Like our other subsystems, the tracking services also works off Kafka using events, And the progress computation and summarization is actually done in an async fashion to ensure that there's no latency while the user waits for this to happen. And once a user has completed, a course or a tracking collection, a trackable collection, there is a capability where, the creator of that collection can actually attach credentials to the collection, which will get issued. And the credentials are configurable to be given to users who have, based on various rules, where it could be dependent on, let's say, the amount of progress you've made on the collection, or even you could even issue merit certificates, which are decided based on the score, the assessment scores that you have actually, got while consuming the collection. We also have the capability to extend the tracking system via these jobs and via the extension points and events to allow for something like, let's say, if you want to allow users to be giving certificates only if the user has spent a stipulated amount of time, going through the content, that's also quite possible through an extension. And the batch data is actually indexed into Elasticsearch for enabling searching. For the tracking data, it's stored only in Cassandra, because we've seen that Cassandra is best at storing huge volumes of transactional data and a linearly scalable engine. And again, Redis is used for transient caching. Okay, moving on. The collaboration subsystem actually takes care of cohorts and the various activities that users can do within cohorts. As of now, we have allowed for consuming trackable collections in a group, and also enable discussion forums. And each of these leverage open source stacks. For example, the discussion forums are, wrappers built on top of NodeBB, which uses MongoDB as its data store. And while building these wrappers, we have ensured that they integrate with Keycloak, which is our authentication engine, and also with the telemetry specification, so that we actually have a view on what's happening, how are users leveraging the discussion forums. And the group functionality, or the cohorts functionality, is implemented in a plugin fashion, so that you can actually add more activities, which will be made available to these cohorts once you're able to link these activities to these groups. Talking about the chatbot, we are leveraging OpenRasa, which is an open source NLU engine, which uses Redis as its session store for contextual sessions of users. And Rasa, it can be easily embedded, to allow for natural language understanding, and it's quite easy to train for the various, contextual chat use cases that you may have. Again, while integrating Rasa, we have ensured that, the system can send telemetry, and the system can scale by horizontal scaling. Okay. Moving on to the client apps, we've seen a session by Santosh yesterday where, we had a detailed walkthrough of the client apps architecture. So I'm not going to delve into details here. As you can see, we're using Angular 8 for the UI components and widgets. And we use a combination of TypeScript, and we use service interfaces to ensure that the services can switch between Cordova when the context is a mobile app versus Node.js when it is a desktop app, or the server-side APIs in a portal-like scenario. So it's Ionic is used for packaging the app for mobile app use cases, and Electron is used as the packaging engine for the desktop app. Okay. Moving on. So by now we have actually looked at the various text components that are used while we have built all these subsystems in Sunbird. And I just want to highlight why we have chosen some of these stacks. So Neo4j, for example, is open source graph, which is and the largest known installation of Neo4j, the largest published installation of Neo4j, supports 1.5 billion graph objects. Likewise, Kafka, which originated at LinkedIn, is used at LinkedIn to trigger data pipelines which process up to 1 trillion messages a day. And likewise, Elasticsearch powers the GitHub search, and it has about 17 terabytes of data, which is able to process easily. And the transactional data, we've chosen Cassandra, which is a near linearly scalable NoSQL, which can, and the largest node installation of Cassandra has about 75,000 nodes and, a huge volume of data. Now, it's not possible to assume that just by adopting these tech stacks into subsystems, we can kind of get the same level of scale that these references provide. It is equally important to benchmark and prove that we've adopted the best practices and the patterns and avoided the anti-patterns that can probably cause scaling issues. So we have done our own benchmarking on Sunbird, and we have seen that, millions of graph objects with millions of relations are still possible with the way we are using Neo4j. Likewise, we have a data pipeline which is capable of processing 2 billion messages a day, and we know that it can scale linearly beyond this, but it's just that we've benchmarked it to this capability. And we are using a 7-broker Kafka cluster, which scales in comparison with 1100 brokers used at LinkedIn. But we are able to handle a peak of about 200 messages, 200 million messages every hour. And our search indexes in our load testing environment have about 1 billion docs ingested, and the data size is about 2 terabytes, again on a 6-node cluster. And with Cassandra, we have actually gone to the extent of ingesting about 5 terabytes of data. With some of the, like for example, the tracking data stores actually get a lot of records for every user's content access within a collection. So we have actually benchmarked it for billions of records and ensured that, the API response times when we have all these kind of, millions and billions of transactional data is still sub-second. And all the load testing that we have done and all the scripts and the sample test data is actually available on GitHub. While this should give you the confidence that the system can scale, if you are setting up Sunbird, you can also leverage the scripts and the test data here to benchmark how your environment compares with the reference scale that we have provided here. Okay, so moving on. At this point, we have covered the various subsystems, and we've seen what are the tech constituents, and we've also seen that they've been benchmarked to be sure that they work at scale. Now, we will look at how a request response lifecycle in Sunbird looks like. Now, we've not just packaged software and subsystems in Sunbird. I also spoke about the solid DevOps and Infra foundation. So we've also embedded components which allow us to adopt and provide, the infra best practices for sharing between adopters of Sunbird as well. So here's a sample request flow in Sunbird. So you have the client apps which actually make API calls to the Sunbird backend. We have a load balancer, which is obviously part of the infra that you set up. And the load balancer just sprays the request to a reverse proxy. The reverse proxy plays 2 roles. One, it acts as a proxy for the static assets which are stored in blob. It also routes the API calls to Kong, which then takes care of the authentication and rate limiting and forwards it to the various microservices or subsystems in Sunbird. Now, why did we choose to embed an Nginx and Kong layer instead of asking users of the platform or adopters of the platform to just set it up themselves? This allows us to pre-bake and ensure that the best practices that we have come across in our benchmarking and the best practices that we see other adopters who have taken this platform to scale can be brought in and made available to the newer and the latest adapters in the field. So if you look at the proxy, we have introduced caching capabilities. We also ensure that some of the APIs which are not changing frequently, some of the metadata APIs and master data APIs, they are cached on the proxy. So we are ensuring that that load does not come onto the microservices. The proxy also takes care of caching the static assets which we don't want to be going to the blob storage for every user request. Instead, the commonly used assets are cached on the proxy, and the proxy is really efficient at doing that. We have ensured that Kong is able to take care of authentication with an access control list, so we can define which clients have access to what APIs, and access control is tightly controlled. We also have rate limiting and capabilities to request to control the request sizes for the various requests that are coming into Kong. And on the proxy, we also have request mirroring capabilities. Now, what I mean by request mirroring is, let's say you are having a production issue, and you want to know, what is the request that is causing an issue. In a normal, in a normal running system, you may not want to mirror or log all the requests that are coming to the system, because on an internet scale system, that will be huge. So we have the ability and flags to turn on mirroring and select logging based on your needs. You can do it for select API routes, or do it for all APIs if required. And we also support request tracing, which means that when your request comes into the proxy, a UUID is generated and attached to the request as a header, which then gets propagated into the various subsystems. And these subsystems actually log this trace ID in all the logging that they do. So for an end user, for somebody who's managing the system, it's quite easy to understand the life cycle of a request. It can actually traverse by looking at the logs. It can actually look at the various subsystems that the request has gone through. And we have also taken care of embedding, some of the best practices. Like, for example, we know that at scale, using keep alive connections instead of creating newer connections for every request, every user request, is going to have significant CPU savings and reducing latency. So we have ensured that all the connections between the proxy and Kong are using keep alive connections, and from Kong to the upstream services are also on keep alive connections. And we don't expect our microservices to be doing any response compression, because that's also handled on the proxy. We actually enable responses which are above a certain threshold, which is configurable, to be auto compressed by the proxy before it's sent out to the out of the data center. And the proxy, having a proxy which is part of the stack, also helps us implement some of the best practices, like rate limiting the number of open connections from a single IP address, to avoid simple DOS attacks. It also ensures that we are able to control the the TLS versions that are supported, and also blacklisting the weak ciphers which are to be blocked and not allowed while clients make SSL connections onto the proxy. And because we have ensured that the proxy is actually terminating SSL and and handling the connections, the load balancer, you could actually use a layer 4 or a layer 7 load balancer, and it doesn't matter, because the proxy is going to take care of ensuring that the the SSL is terminated at the proxy, and the routing is also handled there. We also have some experimental GeoIP capabilities. If you are able to put in some GeoIP addresses, you could actually control traffic from, you could decide to choose countries from which you want to allow traffic. So this is the way a standard request flows into Sunbird. And by having the proxy and Kong in there, we are able to ensure that the microservices get all these benefits without really worrying about these cross-cutting concerns. And one key thing about having the Kong and proxy is the metrics that we are able to generate. We have also ensured that the proxy and Kong generate metrics which help us, compute the request, the live real-time request per second, the average response times, and also the response codes. This data is actually scraped by our monitoring stack, which actually allows you to see all this data, and this is very important when you run a system at scale. So moving on to the monitoring and the log aggregation. So here, if you look at the Sunbird stack, you can broadly classify the services as Linux processes which are running on VMs. The databases and Keycloak are examples of such processes. And the rest of our microservices are all containerized and running on a Kubernetes cluster. So, I would want to just highlight some of the components we have embedded into our monitoring and logging stack to ensure that any new VM or any new service that gets added into Sunbird by us or by the ecosystem is actually coming under the purview of monitoring and log aggregation. So we have automation to ensure that any VM that gets spawned will have Monit and FileBeat and node exporter deployed. So Monit is used to ensure that it can restart the processes if the process gets killed. FileBeat is a log shipper, which can look at the log files and ship it into Elasticsearch. And node exporter is a process which actually makes your node CPU memory metrics available to Prometheus. So we've used Prometheus as our strategic monitoring tool, and Prometheus is able to scrape or pull these metrics from the various exporters to kind of aggregate the data and then show Grafana dashboards where all this data can be viewed. Now, apart from node exporter, which is used for looking at VM metrics, we also have specialized exporters which we have integrated. Like we have a Cassandra exporter, which can actually give you details about the Cassandra cluster, the amount of compactions happening in Cassandra, and a lot of insights into the read latencies and write latencies in Cassandra. So, and it's not that we have solved all these problems and we have exporters for all the tech components that we need. That's a good area for contribution. For example, for the Elasticsearch, we are actually not using an Elasticsearch exporter, and that's definitely something that can be easily integrated. And talking about the Kubernetes nodes, we actually have node exporter deployed, just like we have them on the VMs to give out VM metrics. And we use FluentBit and Prometheus operator, which actually integrates with the Kubernetes API server to pull out metrics on the various pods or services that are running in Kubernetes. And it's able to make this data available on Grafana for consumption by the NOC team or the team which actually manages the infra. And you can see in the diagram that there's an alert manager which actually is able to query the data from Prometheus in a periodic fashion and can raise alerts, and it's configurable. You could, for example, set alerts to say that you want to be alerted when the threshold of let's say 500 response codes go above a certain limit. Or you could say that you want alerts when you want disk usage crossing, let's say 80%. So all that is possible using the alert manager, leveraging the data in Prometheus. And FluentBit is used as a log shipper for the pods. So all the pods which are running on a particular node will write the logs to the standard out, which will get ingested by FluentBit into the logging stack. Okay, moving on. So now that we have covered, the various tech components, we have looked at the request response lifecycle, and we have also looked at the monitoring stack. Here's a view on how the deployment looks like for our microservices layer. All the components in here should be familiar to you by now, so we have the load balancer, which ingest the traffic into a Kubernetes cluster where the proxy receives the traffic, and then the proxy takes care of routing the traffic between all the various other microservices via the API gateway. And in the case of the portal, we have a portal backend, which actually receives the traffic from the portal client, and that will route the API calls via the API gateway to the rest of the microservices. And as you can see here, we have the databases and the Auth server, which is outside the Kubernetes layer. So it's still running on VMs. And we're trying to see what more services can be pulled into the Kubernetes layer. And this is the deployment view of the data platform that we saw earlier. So again, the data pipeline jobs are also run as Kubernetes pods. So they are all Flink jobs where these jobs run as pods in a kube cluster and are scalable easily. It also helps manage them easier. And broadly, there are three main steps in the data pipeline. One is the extraction, which is extracting the compressed data and deduping them as well, because we allow the clients to retry sending of telemetry till they have received an acknowledgement from the server. So it's quite possible that we get duplicate events, and that's why the dedupe is very, very important. And we have a preprocessor which actually ensures that the events are adhering to the spec. And then we have a denorm job which actually takes care of enriching the events with the user context, the content context, and location, and other information that is necessary for the real-time metrics. And the data, I've explained before, the data is actually backed up to C core, and Spark using C core to the blob storage, and Spark pulls the data from the blob storage and computes metrics and summaries which are ingested back into Kafka, and then that's also ingested into Druid. But that's more of a batch mode. So you can think of the data platform as a Lambda architecture where the streaming jobs and Druid form the speed layer, and the Spark jobs form the batch layer. And again, superset is used to visualize the data in Druid. So while we've seen the tech stack, we've seen the various components, we've seen how they work together, we've seen how we have also embedded infra components to ensure that the best practices come in. Now, this stack has to be deployed on it can be deployed on any cloud following the best practices for the cloud. And this will ensure that the security aspects and the scaling aspects that we have taken care of in the software level are available to you. So what you're seeing is a recommended cloud blueprint where, this is a blueprint which says that you have actually got two environments. You have a test environment and a production environment. And we want the networks to be separated. So you can assume that there should be at least 3 VLANs, virtual networks, one for the admin, where you will have the Bastion host or Jump host and the CI systems to build and for your CI/CD processes. And you would have separate VNets for each of your environments that you want to run. So here we are showing that you have 2 environments, so we're seeing 3 VNets in total. And you could set up on any cloud that you're in, you could set up network rules between these VNets to ensure that traffic is only allowed on certain ports from one VNet to another. So there's, security is something which can always evolve, and there's no limit to the amount of additional rules you can put in to ensure that your infra is more and more secure. And we recommend wrapping the entire infra over a VPN, which implies that none of your infra components should have a public IP associated with it. Your public IP can only be attached or should only be attached to the load balancer, which can, so your domain can be mapped to the load balancer. And, ensuring that if you follow this blueprint, it ensures that, you kind of get a system which is proven to be safe from vulnerabilities. And we have got these blueprints, we brainstormed these blueprints with a lot of cloud security experts. And we've also done an external validation of one of our environments to be sure that it meets the necessities of a secure system. Okay, and while this one is about how you separate the VNets, the next one is going to be how you, within a VNet, how do you break them into subnets? So again, within a VNet, we recommend having subnets for admin. The admin subnet is again, where you will run your CI slave, which can take care of running the deployments and the automation, and a Bastion host, which is required in the rare case of somebody having to SSH onto one of the VMs in your VNet. And like I've shown, the Kubernetes agent nodes are a separate VNet with the non-containerized workloads in a separate VNet, and there can be security groups between each of these subnets to decide what kind of traffic can flow between them. And the external load balancer is attached directly to the Kubernetes agent nodes with only port 443 or port 80 attached, and that will ensure that the rest of your infra is secure. And the databases can be in their own layer. So with this, with this recommended blueprint, anybody who is trying to host their instance of Sunbird, you get the assurance that your infra is secure, and you also get, a software tech stack which is tested at scale and secure. Okay, so that is pretty much what I wanted to cover. I hope this has given you the context to get exploring further on Sunbird. The entire source code and automation is available publicly on GitHub, and you can find the references to that on the Sunbird portal. With this, I hand over back to Madhu.
Hey, thank you, Mathew. Thank you, Mathew.
Thank you.
Seriously, a power-packed session. I mean, you cut across right from the fundamentals of the architecture to the various tech layers, the components, our entire architecture piece, and how to actually deploy it. So it's really a capsulized piece of the architecture that you actually put across over here. But I really want you to stay back for the next 10 minutes or so. We have quite a few questions that have come up in our Q&A box. I'll actually request Railu and Santosh to also come as panelists, and then we could distribute a lot of these questions that have come up over here. So I'm just going to take a few seconds to just go through these questions that are there in the box. I see a question from Venkat where he's asking about, okay, I'm just going to go a little silent. So let's just paraphrase this question. I think it actually is about, why Sunbird is using so many technologies and what is the reason for choosing so many technologies. Mathew, will you want to take that question?
Sure, Madhu. Yeah, so as I said, we are using, a lot of tech stacks. We've ensured that the best practices in these tech stacks are adopted for all the subsystems that we build. And we like to use the best tool for the job, because when you have to scale, when you have to build a scalable system, you cannot restrict your mindset to be just using a relational database or not using a queue or things like that. So by leveraging these tech stacks, we actually get the best options available in the open source fraternity, and we are able to leverage this to build a system which can scale out almost linearly. So while there is a complexity in running that, we have tried to ensure that there is enough automation so that anybody who's adopting Sunbird does not have to worry about these individual tech components, and the system is glued together to be able to run as one unit with the ability to see when something goes wrong so that you can just tackle what has gone wrong. So while the tech stack might look like a huge list of things, if you really break it down, we've ensured that there is the manageability is at the core of everything that we do. So I still think that, while if you are trying to use it for a very small use case, it might be counterproductive, but for use cases which have to scale to thousands or lakhs of users, such a system, such a platform which is extensible, which uses the right tools for the right job, is extremely important.
So Mathew, what I'm going to do is I'm just going to ask a question in my way also right now, all of what was just asked. So are you saying we can use Sunbird in an a la carte way? Is it possible only to take some of the components?
Yes, it is. So like I said, we refer to each of our subsystems because each of them can have an independent evolution. Now, we have seen adopters who have discarded the user and org subsystem, which Sunbird comes with out of the box, and being able to embed their own user and org systems. We've also seen them being able to integrate with Office 365 instead of leveraging an OpenID provider like Keycloak. So all these are possibilities. While we may not have tested and proven this, it is we have adopters who have actually used it at scale and are successfully using it live.
So I'm just going to ask a question somebody else has asked, and this I'll request actually Riley to answer this. Riley, the question is, why did we choose an ontology-driven approach?
Okay. See, the core Sunbird is for, the premise of Sunbird is for supporting learning. And the learning is not a very simple thing. We need content from different types of content for different purposes, like an introduction content, a practice content, or drill down content. and for different concepts. So you need to classify all your content, concepts, entities in proper categories, and also have relations between them so that you can use all this content and concepts and give an effective learning to the end user. And ontology is a science, computer science aspect which enables all these kind of relations and describing entities in a well defined manner. That's why I mean the core engine is an ontology based engine which enables us to model different types of pedagogies using the same platform. Yeah.
Okay. Mathew, I'm going to come back to you. There's a question from Saket for non-containerized VMs. How is horizontal scaling being done?
Okay, so it's slightly more difficult than running pods in Kubernetes, obviously, but we have automation. We have 100% automation for provisioning any of the tech stacks that we have used. Like let me take two examples. Let's say we have Keycloak, which is running on VMs, and we have Cassandra, which is running on VMs. And we have dashboards, Grafana dashboards, which actually show the utilization, so you will know when, either CPU or memory or, disk IO is throttling. And you could also get a view of, how the systems are working by looking at the response times from APIs. So let's say that you detect that there is a problem in one of those databases or Keycloak and you want to scale out. It is as simple as, running some cloud automation templates to get new VMs. And the moment you have a new VM, it's just a matter of adding the IP address of that VM into your inventory, because we are using Ansible as our configuration management tool. And you could just run the provisioning jobs, and those provisioning jobs will provision Keycloak or Cassandra and help them add into the cluster. So while it still requires manual intervention to trigger these jobs, but it is automated, and you really don't have to know the internals of Cassandra or Keycloak to be able to add more nodes and scale out the cluster. And we've ensured that all the tech, databases and the various components that we use are scalable by adding, horizontal nodes.
Thanks, Mathew. Santosh, one for you, again from the list of questions that have been asked. To read it out verbatim, for offline mode, where exactly the user tracking information is stored? What about size?
Okay, so user tracking information is stored locally in its local SQLite database. And see, for a size perspective, what we do in the sense that for us, we have a effective storage management built into the app itself. And we also only store, when you say tracking, it's only whether it's the content is completed or not. And users, courses, the number of courses will be anyway too small. Okay, and the other thing what we do in the sense that we periodically always sync the data back to the server and we refresh back from the server. So users are free to go ahead and clear up the storage and again refresh back the data from the server again. For the courses they are trying to go through, it's also a little bit intelligent enough as well.
Okay, one more question, and Riley, this is for you again from the list of questions. For a poorest of poor students, just having a feature phone, what all these features are okay for them?
Yeah, okay. See, primarily Sunbird is mainly supports smartphone. Most of the features are work only on smartphone, but we are slowly working on capabilities like where you can print the content back. There are no features specifically for feature phones, but we are making building features so that people who don't have access to digital devices can also use these features, like printing the content and using the printable formats. Also, we recently launched this desktop app where schools or any communities around people can have these desktops and the content and everything can be loaded. So the people can go there, log in any of those desktop, which is again offline, which works again offline, use the Sunbird features in it, and they can come back and use any of the community devices, desktops at schools or libraries to access Sunbird. Uh, so that's how we are trying to reach the market which is outside the smartphone. But yeah, still there's a long way to go in that area for us. Yeah.
Thanks, Riley.
Yeah.
Mathew, one for you. Does Sunbird isolate the data of multiple tenants?
No, it's a logical isolation. The PII data of users is stored encrypted. And we have various framework level aspects to ensure that data of tenants is not accidentally exposed by a different tenant. For example, if you have a role to a specific organization, we have a framework level, or it's embedded within the microservices to attach the scope in all data fetches, so that you are not able to get data for other tenants. And there is validation in terms of the tokens which actually come into the microservices. The access tokens which come in actually specify the roles and the scope, and so you can only fetch data for that scope.
Sure, thanks. Mathew, I'm just going to request you to answer one more. This is from Deepak, and this is about the security tools and primarily the security that has been built around it. So it's a logical extension to your presentation. If you could just spend 2 minutes on that.
Yeah, so I've already shown the slides, the request response lifecycle, the flow path within Sunbird. So by embedding a proxy and Kong, we are actually able to ensure that you have user authentication, rate limiting, and some of the security best practices already in place. Apart from these, for the functional workflows that we have implemented, we have also done Google reCAPTCHA implementation to be sure that critical workflows like the sign up, the forgot password are actual human beings and not bots. So we have actually put in some of those checks. And on the proxy, we have put various levers to actually control which countries you can allow or deny traffic from. Again, this is something where you will have to get a device, an IP database from a provider. That doesn't come in Sunbird out of the box. So we have all those capabilities in portal in our proxy. And while we were getting this externally validated for a vulnerability assessment, there's some other detailed best practices, like not exposing certain request headers, not allowing certain characters in the path. So there is a fair bit of those practices also embedded within some of these proxies.
We're really running out of time now. I know there are many more questions that are there in the box which are not answered. However, firstly, thank you for actively participating and asking all of these questions. My request is for all of you to take these questions to the community forums and actually ask them over there, and you will definitely get responses to the questions that have remained unanswered in this forum right now. So again, requesting you to encourage you to actually actively use the community forums for any clarifications, any queries that you would have. And I can assure you that the forum is very active. Again, to repeat, and as all of you are aware, all of the source code is open sourced and is available on Git. And if there are architects and developers listening, and we would actively encourage you to go there and have a look at our Git repositories. So all of these details are also available on our website, sunbird.org. So request you to go there and keep it active with a lot of questions that you have and looking up at all the details over there. So thank you all. Thank you for the time. It's been an amazing 1 hour. It's been quite interactive with a number of questions that I see over here. Really, thank you for spending this 1 hour with us on the tech session.